these out, I'll have you work one out, and then I'll give you 2 problems to do on your own. Okay? So on this one, we have a compound that's going to go through a combustion reaction, because when you have a compound that's got carbons and hydrogens, in general, that kind of gives you an understanding that it's going to be a combustion reaction. And anytime you produce CO2 and H2O, that's another indication it's a combustion reaction as well. So what we have is we have a compound that's CXHYOZ reacting with oxygen, and it's producing CO2 plus H2O. Okay, so that's what's being produced, and the amount of CO produced is 8.369 grams, and water produced is 3.461 grams. If you notice, the amount that we start out with is 3.101 grams. So you're like, well, I don't know how that works. You're producing a lot of CO2 and we got only 3 grams on the left side. What's missing information that we're not going to have to worry about is this amount of oxygen right now, because the oxygen that we need to find in this compound we'll be able to find by finding the amount of carbon and hydrogen percentages. So if we can find a percent of carbon that went from here, because it only goes to one spot. The carbon here goes to the carbon over here. And then the hydrogen here will go to the hydrogen here. But the oxygen here will go to one of those 2 spots, plus we add in oxygen. So as long as we can find carbon and hydrogen percentages, then we know oxygen's percent, because it's the missing percent to make the 100% up of your sample. So the first thing I would like you to do on your own, I think you guys can do this. We'll see if you remember. But I want you to find the grams of carbon in this sample of CO2. So this is the grams of CO2. What I want you to do is find the grams of just carbon that makes that sample up. Let's see if you can do that. I'm going to give you a couple minutes. If you can't do it, I'll show you. Find the grams of carbon based upon a sample size of CO2 of 8.369. Okay? Go ahead and do that. We did a problem similar to that on a previous worksheet. Okay, the answer you should come up with is 2.28 grams. You may get it? Did you get it? You may get 2.28? Nobody? No? 2.26? 2.26? Okay, you probably did it right then. So, the way you would do it, easy way to do it, you could find the percent of carbon in CO2, right? So you could actually take 12 divided by 44 times 100, and you'd got an answer of 27.3%. And then you could take that percentage times the 8.369, and by doing that, then you get you 2.28 grams. But if you want to do it all in one step, what you do is you say, okay, I've got 8.369 grams of CO2. I'm going to say that for every 44 grams of CO2, I have 12 grams of carbon. That's a ratio, mass to mass. So,
okay, so the 44, is that just the molar mass of the thing?
Yes. Okay. So what you can do, now all this is doing is multiplying it by the percentage. If you take 12 divided by 44, you're going to get 0.273. Okay? And then if you take that times 8.369, that gives you the amount of carbon. So it's 2.28 grams. Eric, did you do something similar to that?
Yeah.
Okay.
I just left out the 0.3 on the percentage.
Okay. So 2.28 grams. Why don't you see if you can use that same method for finding hydrogen in water? Okay, so you go ahead and try to find the amount of grams of hydrogen by mass in 3.461 grams of water. Okay, go ahead and do that one. So on the water, you take the 3.461 grams of H2O. You say for every 18 grams of H2O, you have 2.02 grams of hydrogen, which that'll give you a decimal form of the percent. And then you end up with an answer of 0.386. So I'm just going to put that down here, 0.386 grams of hydrogen. All right. Any questions on this? So, the only thing that we need to find is the grams of oxygen. So, we have grams of carbon, we have grams of hydrogen, and we got the total grams, because we know that of this 3.101, we've got 2.28 grams of carbon in there. And we also know within that 3.101, because of conservation of mass, all the hydrogens that went over, there was 3.86 grams of hydrogen that went over from this 3.101. What you can do is you can find oxygen by subtracting out those two weights from the total, right? Because if you know carbon, okay, you know the carbon here, the weight, you know the hydrogen, the weight, the only thing you're missing is oxygen, and then this is all three of them combined. What you can do is you can take 3.101 and subtract out the 2.28 grams of the oxygen, and also subtract out the 0.386. I get that in there, right? 386 grams of hydrogen, and this is the total. You're going to come up with oxygen's weight. Okay. So what is oxygen's weight? 0.43 grams, right? Any questions on that? So all three of those added up, 0.43, 0.386, and then 2.28 grams, it adds up to the 3.101 total. So guess what you can do now?
What are we looking for?
You are going to find the empirical formula. It's not stated up here, but you got to find the empirical formula. You got to find out what the empirical formula is of CHO. So now try to find the empirical formula with those weights. 2.28 grams of carbon, 0.386 grams of hydrogen, and 0.43 grams of oxygen. And this is practicing empirical formula. So we went through that work in which to find the weight of everything so that we can convert it to moles, and then we can convert it into a formula. So go ahead and do that if you would. These compounds, carbons and hydrogens, most of the time you're going to have a lot of hydrogens. And you're going to have a lot of carbons, and the oxygen is the one you're not going to have as much of. So oxygen is usually going to be the one that is going to be the lowest number of moles that you will divide into the carbon and hydrogen. Because when we look at these compounds, they are longer chains of carbons hooked together. So we've got multiple carbons hooked together. We've got a lot of hydrogens associated with that carbon chain, and then a lot of times our oxygen is going to be a smaller amount. Okay, usually like 1 or 2. Usually the case. It could be more than that, but nobody says it couldn't be more than that. But usually that's going to be the case. up and you're kind of looking at your numbers, and I didn't go as far as maybe you have went. Maybe some of you went farther. When we look at this, you can see that hydrogen's double carbon, right? You know when you come up with a formula that hydrogen has to be a subscript twice as much as carbon. And then oxygen is just a small amount. So if I take and divide by the smallest number on all of these, I get some numbers that some of them are close to whole numbers and some of them are a little bit further away than what we're used to. And I'm going to try to help you understand why maybe we can not be as close as we normally think we have to be on these. Now this is experimental data. That's not perfect. That's kind of like the experiment that you guys have done. And so when we figure out our formula, we realize it's probably not going to be a perfect situation where these will come out perfectly whole numbers that we would like. Okay? So when you do oxygen, of course, it's 1 oxygen. So we get 1 mole of oxygen. Okay? So then when we do the carbon, we get this number that's 7.06. Is that what you guys got? Something close to that? And then when we do the hydrogen, so I'll put carbon there, that's oxygen. And then when we do the hydrogen, I came up with 14.2. Did you guys come up with something similar to that? Mm-hmm. Okay, and so some of you get concerned about that, and you should be. You know, we want numbers really close to whole numbers. But if we know it's double carbon, then we could just make that 14. Does that make sense? Because we know carbon is 7.06. That rounds down to 7. We know that there's not much difference between if we double this number, we get if we double the carbon, we get 0.38, and that was 0.382. So hydrogen is one of those that it could be a little bit off just because when we round, it could cause a little bit bigger difference in our moles of our hydrogen. The hydrogen is going to be the one that's going to give us problems because it's probably not going to be as close as the other ones are going to be. Just because we're dividing by 1.01, okay? And the other ones we have bigger numbers we're dividing by, which allows us to have a little bit more play. So what would be the chemical formula for that? The empirical chemical formula would be what? C7H14. Now, if you were really good and you knew your organic chemistry and you go, well, I don't know if that's even possible, you would put together that molecule and realize hydrogens have a 1 single covalent, carbon has 4 single covalents it can have double bonds too, and then oxygen's going to have 2 covalent bonds with it. And you could actually write it out. You would be guessing what the formula would be, the structural formula would be, but you could write it out, and then you could logically see what the possibilities are for it. The longer the carbon chains, the tougher it's going to be to do that. Okay. So what I'm going to do, instead of doing another one, I just have 2 examples that I'll have you guys run through on your own. You can run through one of them in class and check your answers before you go, and then you can do the other one. You can do the other one on your own, okay?